Tonight, we're going to talk about something that is happening right now while you listen to these words. Not a slow, distant, someday kind of event. Something active, ongoing, continuous. Somewhere out past the edge of what any telescope will ever be able to prove, galaxies are vanishing from our reach at this very moment. Not by exploding, not by colliding, not by any dramatic event at all. Simply by drifting, quietly, past a boundary they can never cross back over. Here is the number that should stop you cold. Of everything we can currently see in the night sky, every one of the roughly 2 trillion galaxies scattered across our entire observable universe, approximately 94% of them are already gone. Not too far away to see. We can still see them, tonight, through a good enough telescope, but gone in every sense that actually matters, permanently unable to send us anything new ever again for the remaining lifetime of the universe. Only about 6% of what fills our sky remains within our reach at all. And it isn't a fixed loss, either. It isn't 94% today and 94% forever. It's growing. Right now, tonight, while you listen, something in the neighborhood of 160 billion stars, roughly one entire large galaxy's worth of light, is quietly, permanently crossing that boundary, joining the already unreachable majority every single year. But here's what most people don't realize, and it's the strangest part of the entire story. Those galaxies don't simply blink out of existence the moment they cross that line. We keep watching them. For billions of years afterward, sometimes. Their light keeps arriving, keeps reaching our telescopes, growing fainter and redder and slower with each passing year. Behaving, in fact, in a way that should sound eerily familiar if you've ever heard how physicists describe something falling into a black hole. The first surprise is that there are 2 completely different boundaries hiding inside the phrase observable universe. One marking what we've ever seen, another marking what we can still ever learn anything new from. And they sit at 2 dramatically different distances. The second surprise is the precise mechanism by which a galaxy fades from our view entirely, not vanishing, but stretching. Its light and its very time itself smeared out toward an infinity we will never quite watch it finish reaching. The third surprise is that this isn't some far future concern, safely distant from our own lives. It's happening today, this year, continuously, while the universe around us keeps accelerating faster with every single year that passes. And the fourth surprise, the one that reframes the entire story, is that we happen to be alive during the single best moment across the universe's entire multi-hundred billion year future to actually witness any of this at all. By the end of tonight, you're going to understand exactly why the universe is disappearing, how fast it's actually happening, what it looks like when a galaxy crosses that final threshold, and why the fact that we can watch it happening right now is one of the more remarkable pieces of cosmic timing our species has ever been lucky enough to inherit. Before we dive in, if you're someone who finds real comfort in understanding the true scale and structure of things, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start with the basic shape of what we're actually able to see, because the very first number in this story is already stranger than it has any right to be. The universe is 13.797 billion years old, measured with extraordinary precision by the European Space Agency's Planck satellite, accurate to within about 23 million years either way. Given that age, a reasonable person might expect the observable universe, the total sphere of space whose light has had time to reach us since the beginning, to have a radius of roughly 13.8 billion light-years. Light travelling outward for 13.8 billion years should define a sphere of exactly that size. Instead, the measured radius comes out to approximately 46.5 billion light-years. The full diameter, 93 billion light-years, or about 28.5 gigaparsecs, in the units cosmologists tend to use, more than 3 times larger than the age of the universe alone would suggest. The reason comes down to something we need to sit with carefully, because it's the foundation everything else tonight depends on. While a photon has been travelling toward us for, say, 13 billion years, the space it was crossing has not been sitting still the entire time. It has been stretching continuously in every direction for that entire journey. The distant matter that originally emitted the earliest light we can now detect, the light that makes up the cosmic microwave background, the oldest light that exists anywhere, has, in the time since it was emitted, been carried outward by that same stretching to a present-day distance of roughly 46.5 billion light-years. The light took 13.8 billion years to reach us, but its source is no longer anywhere near where it was when that light began its journey. Picture a swimmer setting out to cross a lake that is slowly, continuously widening beneath them the entire time they're swimming. By the time they finally reach the far shore, the shore they originally left behind has drifted considerably farther away than the actual distance they swam to get here. That gap between how far they swam and how far apart the two shores now sit is exactly the gap between 13.8 billion years of light travel and a full 46.5 billion light-year present-day distance. There's a genuine, unresolved wrinkle sitting underneath even this foundational number, worth being honest about before we go any further. The precise rate of the universe's expansion. The Hubble constant, which determines exactly how quickly that widening lake actually grows, is measured 2 different ways by cosmologists, and those 2 ways currently disagree with each other. Analysis of the cosmic microwave background itself, using the Planck satellite's data, gives a Hubble constant of 67.4 plus or minus half a unit in the standard kilometers per second per megaparsec notation. But direct measurements of nearby galaxies, using a completely different method built around pulsating stars called Cepheid variables, consistently return a noticeably higher figure, 73.04, plus or minus about 1 unit. This disagreement, now measured at roughly 5 standard deviations of statistical confidence, a threshold that in most fields of physics is treated as the formal boundary for declaring something a genuine discovery rather than dismissing it as coincidence, remains, as of this telling, entirely unresolved. Cosmologists call it the Hubble tension, and it's one of the most actively debated open problems in the entire field. As for the true size of the whole universe, beyond just the portion we happen to be able to observe, it may well be far larger still, or genuinely, mathematically infinite. Measurements of the universe's overall spatial curvature, combining data from Planck, an earlier satellite called WMAP, and a balloon-borne experiment called Boomerang, find it consistent with perfectly flat to within about 0.4%. That result is fully compatible with an infinite universe. It does not prove one. The honest answer, as of right now, is that we simply cannot yet distinguish genuinely infinite from very much larger than what we can currently observe. Both remain entirely open possibilities. Hold all of that in mind, because tonight's actual story isn't really about this outer boundary at all, the 46.5 billion light-year edge of everything we've ever managed to see. It's about a much smaller, much stranger, and considerably more urgent boundary sitting well inside it. But to understand why that smaller boundary exists at all, we first need to understand the specific force that's driving it wider apart every single year, right now. For most of the 20th century, cosmologists studying the expanding universe were only really debating one question: exactly how much the expansion was slowing down under the steady, patient pull of its own gravity. Everyone agreed it had to be decelerating, at least to some degree. Gravity is an attractive force. Given enough time, it should always be pulling everything back together, gradually easing the expansion's momentum, the same way a ball thrown upward always slows as gravity pulls it back down. The only real question was the rate. In the mid-1990s, two entirely independent research teams set out specifically to measure that deceleration rate with real precision. One was the supernova Cosmology project, led by Saul Perlmutter. The other was the High-Z supernova search team, led by Brian Schmidt and Adam Rees. Both teams used a particular category of exploding star called a Type Ia supernova as what astronomers call a standard candle. An object whose true intrinsic brightness is understood well enough that its observed faintness from Earth can be used to calculate precisely how far away it actually sits. Both teams reached the same result, working entirely independently of one another, and neither team expected it. The distant supernovae were dimmer than they should have been, roughly 25% dimmer than any decelerating universe, slowing gradually under its own gravity, could possibly produce. Dimmer meant farther away than expected, and farther away than expected, given how long ago that light was emitted, meant one specific, almost unthinkable thing. The expansion of the universe wasn't slowing down at all. It was speeding up. Science magazine named this finding its breakthrough of the year for 1998. In 2011, Perlmutter, Schmidt, and Rees were jointly awarded the Nobel Prize in Physics for the discovery. The force responsible for this acceleration was given a name that, honestly, admits how little we understand about it: dark energy. According to the most precise current measurements, it makes up approximately 68.47% of the universe's total energy content, with ordinary and dark matter together accounting for roughly 31.5%. In absolute terms, the energy density of dark energy is almost unimaginably small, something on the order of 7 times 10 to the negative 30th power grams per cubic centimeter, roughly a millionth of a millionth of a millionth of a millionth of the density of water, spread thinly across every single cubic centimeter of the universe, everywhere, all at once. Here is the property that makes dark energy behave so differently from every other force you've ever directly experienced. As the universe expands, more space comes into existence. And because dark energy's density remains essentially constant per unit of volume, unlike matter, which simply dilutes and spreads thinner as space grows around it, the total amount of dark energy in the universe actually increases as the universe itself grows larger. More space means more dark energy. More dark energy means a stronger overall push, and a stronger push accelerates the expansion further, creating still more space, and therefore still more dark energy, in a compounding cycle that shows no natural sign of ever reversing on its own. Picture gently rolling a ball up a hill, fully expecting it to slow down as it climbs, the way every ball you've ever rolled uphill always has. Instead, halfway up, it unexpectedly speeds up, as though someone had quietly tilted the entire hill in the opposite direction while you weren't looking. That's essentially what the 1998 supernova data revealed about the entire cosmos: an unseen tilt embedded directly into the geometry of empty space itself, patiently working against the deceleration everyone had confidently expected. What dark energy actually is, at any deeper physical level, remains genuinely unknown. It might be a fundamental, unchanging property of the vacuum itself, a cosmological constant in the language cosmologists use. It might instead be a slowly evolving field, sometimes called quintessence, shifting gradually across cosmic time rather than remaining perfectly fixed. It might even be a signal that Einstein's own general relativity needs some kind of modification on the very largest scales the universe offers, scales far beyond anywhere we've ever been able to directly test the theory. Nobody currently knows which of these, if any, is correct. All that has actually been measured with real confidence is dark energy's effect on the geometry and expansion of the cosmos, not its underlying nature. This is the hidden engine driving tonight's entire story, and it's the specific reason that a second, far more urgent boundary exists at all, sitting well inside the 46.5 billion light-year edge of everything we've ever seen. Here is the distinction most people have simply never had explained to them clearly, and it's the key that unlocks everything else tonight. Cosmologists actually track two entirely separate boundaries, and they sound almost identical the first time you hear their names, even though they describe two nearly opposite things. The first is the particle horizon, the 46.5 billion light-year edge we just spent the last section discussing. This is the boundary of everything whose light has ever reached us, across the entire history of the universe. It looks backward in time. It marks the outer limit of what we have ever seen arrive. The second is the cosmic event horizon, and it faces the opposite direction entirely. It marks the boundary beyond which any signal, sent right now, at this exact moment, from anywhere in the universe, could ever possibly reach us in the future, no matter how long we're willing to wait. Its current co-moving distance sits at approximately 16 billion light-years, and in the specific limiting case of a universe governed by a pure, unchanging cosmological constant, that boundary has a definite maximum value it asymptotically approaches, far off in the future. A distance of roughly 17.55 billion light-years, calculated directly from the speed of light, divided by the square root of dark energy's own fractional share of the universe, multiplied by the Hubble constant. Notice what this means, laid out plainly. The particle horizon, everything we have ever seen, sits at 46.5 billion light-years. The event horizon, everything we could still ever learn anything new from, starting right now, sits dramatically closer, at somewhere between 16 and 18 billion light-years, depending on exactly how the boundary is calculated and which specific reference point is used. The reachable region is a considerably smaller sphere, nested entirely inside the much larger sphere of everything we've ever observed. Run the actual volume math, and the implication becomes genuinely startling. Using a reachability boundary of roughly 18 billion light-years against the full 46.5 billion light-year particle horizon, and remembering that volume scales with the cube of radius rather than the radius itself, the ratio works out to approximately 5.8%, matching, independently, the figure researchers actually cite. Roughly 6% of everything within our observable universe remains genuinely reachable. The remaining 94% is already, right now, permanently beyond our reach. Of the roughly 2 trillion galaxies currently estimated to exist within our observable universe, itself a figure with real uncertainty attached to it, since more recent analyses using the James Webb Space Telescope have suggested the true number might be considerably lower, closer to hundreds of billions rather than a full 2 trillion. Only about 6% remain within a sphere we could ever meaningfully interact with again. Something in the neighborhood of 120 billion galaxies. The other 94%, whatever the true total count turns out to be, has already, permanently, crossed beyond any possibility of sending us anything new. It's worth being honest about exactly why this specific percentage stays reliable, even while the total galaxy count remains uncertain. The 94% figure comes from a ratio of volumes, one sphere nested inside a larger one, rather than from counting individual galaxies directly. Whether the true total is 200 billion galaxies or a full 2 trillion, the geometric ratio between the reachable inner sphere and the much larger observable outer sphere stays essentially the same. The fraction is robust. Only the absolute head count remains genuinely up for revision. This is shocking discovery number 1. The observable universe and the universe we can still meaningfully reach are not the same thing at all. They never have been. And the gap between them isn't small. It's the overwhelming majority of everything we can currently see. Picture standing on a beach at dusk, watching a distant ship out on the horizon. You can see it clearly. Its lights are still visible, still glinting across the water toward you, because that light left the ship long ago and has simply been traveling toward you ever since. But if you launched the fastest boat you own, right now, and tried to actually reach that ship, the tide beneath your own hull would carry it away faster than you could ever possibly close the gap. The ship remains visible. It has become, in every practical sense, unreachable. and the water separating you from it keeps widening a little more with every passing moment. Now here's a subtlety worth walking through carefully, because it's the single most common misconception surrounding this entire topic, and getting it right changes how the rest of tonight's story actually lands. There is a specific distance, called the Hubble sphere, sitting today at approximately 14.4 billion light-years, at which a galaxy's recession velocity, driven purely by the expansion of space itself, with no motion of its own factored in, exactly equals the speed of light. It's tempting to assume this is the true point of no return, the boundary past which nothing could ever reach us. It is not. The Hubble sphere is a moving boundary, not a fixed one, and light from galaxies currently sitting beyond it can, under the right conditions, still eventually reach us. Here's why. A photon emitted from a galaxy that's receding faster than light at the moment of emission initially makes zero net progress toward us. Its own forward motion through space at light speed is exactly cancelled out by the expansion of the space it's trying to cross. But the Hubble sphere itself isn't static. As the universe's expansion rate has shifted across cosmic history, decelerating during the universe's early, matter-dominated era, then re-accelerating more recently as dark energy began to dominate, the Hubble sphere has moved along with it, and at times it has genuinely swept outward fast enough to overtake photons that had, for a long stretch, been effectively stuck in place, unable to make any forward progress at all. Once the expanding Hubble sphere passes beyond such a photon, that photon suddenly finds itself back in genuinely subluminal territory, and it resumes making real, measurable progress toward us, eventually arriving, sometimes billions of years later than it otherwise would have. Picture two ants standing on an enormous rubber sheet that's being stretched steadily from both ends. Neither ant is actually walking anywhere. But if the sheet is stretched hard enough, the ants separate from each other faster than either one could ever walk, even at their absolute top speed. Neither ant has broken any kind of ant speed limit. The sheet itself is doing all the separating, entirely independent of anything either ant is doing. This is precisely why the Hubble sphere isn't the true horizon, even though it's the boundary most popular explanations mistakenly reach for, the genuine point of no return. The boundary past which a photon emitted today can never, under any circumstances, eventually catch up to us, no matter how the expansion rate shifts in the future. Is the cosmic event horizon we discussed a moment ago currently sitting somewhere between 16 and 18 billion light-years away? That boundary corresponds to a specific present-day redshift of approximately Ze equals 1.87. Any galaxy currently observed at a redshift beyond that threshold is a galaxy whose light, emitted from this point forward, will never reach Earth. Not in a billion years. Not in a trillion. Never, in the full and literal sense the word deserves. This is shocking discovery number 2. Even among people who have heard that some galaxies recede faster than light, most assume that boundary, the Hubble sphere, is the actual point of no return. It isn't. The genuine, permanent horizon sits at a different distance entirely, defined not by a simple velocity threshold, but by the full, compounding future of an accelerating universe. Let's return to that 94% figure and actually sit with it, because a number this large deserves more than a passing mention on its way to the next idea. Of the roughly 2 trillion galaxies currently estimated to exist within our observable universe, approximately 94% of them, something on the order of 1.88 trillion individual galaxies, if the higher estimate holds, or a correspondingly large majority even under the more conservative post-JWST revisions, are already, right now, tonight, sitting beyond our cosmic event horizon, not too distant to detect. We can, in many cases, still see them perfectly well through instruments like the James Webb Space Telescope, but anything happening to them from this moment forward, any new star igniting there tonight, any galaxy merging with another there this very hour, will never reach us. Their futures unfold endlessly in a place we will never be able to follow. And it's important to understand that this isn't a static, one-time loss, already complete and simply sitting there, unchanging. It's an ongoing, continuous, active process, happening at a specific, measurable rate right now, while you listen to these words. As the universe's expansion continues accelerating, more and more galaxies cross that permanent threshold with every passing year. By one careful estimate, something in the neighborhood of 160 billion stars, roughly the total stellar population of one large, fully formed galaxy, permanently crosses beyond our reach every single year. Not a metaphor. A genuine, ongoing, measurable rate of loss built directly into the accelerating structure of the cosmos itself. Picture, for a moment, 2 trillion candles scattered across a vast, dark plane stretching farther than the eye can see. Every single year, roughly 160 billion of them. A small city's worth of light. Are gently, silently carried behind a slowly receding wall that none of them, and none of us, will ever be able to cross back over. You can still see their glow. The light already in transit hasn't finished arriving yet, and won't for a very long time. But every single one of those particular candles is now, in every sense that actually matters, permanently unreachable. Let that settle for a moment, because it deserves to. Almost 19 out of every 20 galaxies whose light is currently reaching Earth, filling our telescopes, filling every deep field image ever captured, filling the very sky above you tonight, are galaxies we can no longer meaningfully interact with, in any sense, ever again. Not through radio signals, not through any hypothetical future spacecraft, however advanced, not through anything at all. We are looking, quite literally, at the past of a universe whose present, for the overwhelming majority of what fills our sky, has already slipped permanently beyond us. There's an honest caveat worth including here, one that matters for exactly how confidently we should state the raw galaxy count. The widely cited figure of 2 trillion total galaxies traces back to a 2016 study led by Christopher Consolis, extrapolating carefully from deep Hubble Space Telescope images. More recent analyses, using the sharper resolution of the James Webb Space Telescope, have suggested the true total might actually be considerably lower, closer to a few hundred billion galaxies overall, rather than a full 2 trillion. This remains a genuinely active area of ongoing research, without a fully settled answer as of right now. But as we discussed a moment ago, the specific 94% figure doesn't actually depend on which of these total counts turns out to be correct. It's a statement about volume ratios, the reachable sphere against the much larger observable one, not a statement built from directly counting individual galaxies one at a time. Whether the true total is 200 billion or 2 trillion, the fraction already lost to us remains, robustly, somewhere in the same overwhelming neighborhood. We don't know the exact head count, but we know, with real confidence, the shape of the loss. Here is the part of tonight's story that I think deserves the most careful attention of everything we've covered so far, because it answers a question that should, by now, genuinely be nagging at you. If 94% of the galaxies we can see have already crossed beyond our cosmic event horizon, why can we still see them at all? Shouldn't they simply have disappeared? The answer turns out to be one of the more elegant and genuinely eerie pieces of physics in all of cosmology. A galaxy crossing the cosmic event horizon does not vanish in any sudden or dramatic way. It fades, but not the way a light fades when you simply turn it off. It fades the way light fades when it's climbing, endlessly, out of a gravitational well so deep that it can never quite finish the climb. If you've ever heard how physicists describe an object falling into a black hole as observed from a safe distance outside it, this next part is going to sound remarkably, almost unsettlingly familiar. From an outside observer's vantage point, an object falling toward a black hole's event horizon never actually appears to cross it. Instead, as it approaches that boundary, its light becomes progressively more and more redshifted, stretch toward longer and longer wavelengths, while, simultaneously, time itself appears to slow down for it, as measured from outside, approaching but never quite reaching a complete standstill. The object appears to freeze, forever, at the very edge of the horizon, its final image growing dimmer and redder across an ever-lengthening stretch of the outside observer's own future time, without ever technically finishing the crossing from that outside vantage point. A galaxy approaching our cosmic event horizon behaves in an almost mathematically identical way. As it nears that boundary, its light becomes progressively, relentlessly red-shifted, stretched toward longer and longer wavelengths with each passing year. Its apparent rate of time, as measured by us, appears to slow, the same clocks running slower effect associated with gravitational time dilation near a black hole, except here produced by cosmic expansion rather than gravity directly. The galaxy's image effectively freezes in our sky. It doesn't blink out. It dims exponentially and stretches exponentially across an infinite remaining span of our own future. Its very last photon emitted the instant before it crossed the horizon, still technically making its way toward us, still technically not quite finished arriving for the rest of time. Every event that happens to that galaxy after it crosses the horizon is causally lost to us, permanently, forever. But the very last events that happened before it crossed, its final few billion years of history, from our perspective, continue arriving, spread out, stretched thin, growing fainter and redder across the entire remaining lifespan of the universe. Picture an old photograph, left out in strong, direct sunlight for years on end. Its colours don't vanish all at once. They slowly redden and fade and stretch, degrading a little more with each passing season, until eventually only the palest possible ghost of the original image remains, so faint, so washed out, that you can barely distinguish it from the blank paper surrounding it. That is, in essence, exactly what the universe is doing, right now, to entire galaxies, one photon at a time, across a truly vast stretch of cosmic time. This creates a genuinely strange asymmetry, worth sitting with directly. Most of the galaxies currently filling our night sky, our deep field images, our most powerful telescopes, the overwhelming majority of everything astronomers study, are galaxies we can never again affect, never hear new information from, never visit, never meaningfully influence in any way. We are watching, in the most literal sense possible, a slideshow of an audience that has already left the theatre. The performance concluded, for them, from our vantage point, an unimaginably long time ago. We're simply still receiving the house lights, slowly dimming, stretched out across the entirety of our own remaining future. This is shocking discovery number 3, and I think it's the one that reframes everything else tonight. The 94% of the universe that's already gone from our reach isn't gone the way a light going out is gone. It's gone the way something falling into a black hole is gone. Permanently beyond causal contact, yes, but still, technically, visibly, hauntingly present in our sky, fading rather than vanishing, forever approaching a horizon it will never, from our perspective, quite finish crossing. It's worth adding one honest note of caution here. This specific freezing behavior, the asymptotic redshift, the endless fade rather than a clean disappearance, is characteristic specifically of what's called a de Sitter horizon, the kind produced by a genuine, unchanging cosmological constant. If dark energy instead behaves as what physicists call a phantom field, with an equation of state parameter more negative than -1, the far future could look considerably more violent and considerably less gentle than the picture we've just described, potentially culminating in what's sometimes called a big rip, in which the accelerating expansion eventually grows powerful enough to tear apart even tightly bound structures on a timescale some speculative models place around 20 billion years from now. Current data, it's worth being honest, disfavors this particular scenario. The measured value of dark energy's equation of state remains close to -1, consistent with the standard cosmological constant picture we've been describing throughout tonight. But it hasn't been ruled out with total certainty, and 2025 results from the DESI survey have introduced a genuine, if not yet fully conclusive, hint that dark energy's behavior might be evolving over cosmic time rather than remaining perfectly fixed. A result significant enough to be taken seriously, but not yet strong enough to overturn the standard picture. Given everything we've covered tonight, it's worth following this process forward, honestly, into the deep future. Not because any of us will be alive to witness it, but because understanding where this ongoing loss eventually leads gives real weight to the specific moment we happen to occupy right now. Under the standard cosmological model, the same accelerating, cosmological constant-driven universe we've been describing throughout tonight, the process of galaxies crossing beyond our reach doesn't stop with the 94% already gone. It continues relentlessly, compounding further with every passing epoch. Our own local group, the Milky Way, Andromeda, and roughly 80 smaller companion galaxies, all of them genuinely bound together by mutual gravity, will remain intact, immune to this process, because gravity within the group is simply too strong for cosmic expansion to overcome. Current models suggest the local group becomes fully, permanently isolated from everything else in the universe by roughly 150 billion years from now, under the standard model's assumptions. Every other galaxy currently visible to us, the Virgo cluster, the Coma cluster, essentially every one of the 2 trillion, or several hundred billion, galaxies currently filling our observable sky, will, by that point, have crossed permanently beyond detection. The specific timeline, drawn from foundational work by physicists Lawrence Krauss and Robert Scherer, unfolds roughly as follows. By approximately 100 billion years from now, every galaxy beyond our own local group will have redshifted beyond any conceivable detection threshold. Their light stretched so far that it becomes undetectable in principle, not merely in practice, regardless of what instruments a future civilization might build. The cosmic microwave background itself, the ancient relic light from the universe's very infancy, still faintly, patiently detectable today, will, under this same standard model, become permanently undetectable on a broadly similar timescale, its wavelength eventually stretched beyond even the future universe's own horizon. By that point, cosmology itself, as a genuine observational science, effectively ends. A civilization living inside that far future local group, equipped with the most advanced conceivable instruments, would see only their own merged galaxy. The eventual combination of the Milky Way and Andromeda, sometimes informally called Milkomeda, sitting alone against a permanently dark, genuinely empty sky. No cosmic microwave background, no distant galaxies rushing outward to measure, no direct evidence, anywhere, of any kind, that a Big Bang had ever actually happened. That future civilization would rationally, carefully, and completely incorrectly conclude that the universe consists of nothing more than a single, static island of stars, alone, surrounded by infinite, eternal, empty space. And they would have absolutely no way of ever discovering they were wrong. Krauss and Scherer titled their own 2007 paper on this exact scenario, with characteristic bluntness, "The Return of a Static Universe and the End of Cosmology." Now hold that far future picture directly alongside where we're standing tonight. We are not living in that eventual silence. We are living during the specific, narrow window when 6% of the observable universe remains genuinely reachable, when the cosmic microwave background is still faintly, patiently glowing, and when the ongoing process of loss, that steady 160 billion stars per year drift beyond the horizon, is still slow enough, relative to a human lifetime, that we can study it, measure it, and understand exactly what it means, rather than simply inheriting its finished, silent aftermath. Let's gather the actual numbers from tonight, all together, and sit with what they add up to. An observable universe with a radius of 46.5 billion light-years, the full record of everything whose light has ever reached us across the entire span of cosmic history. A reachable universe nested inside it, with a radius of somewhere between 16 and 18 billion light years. Everything we could still, even in principle, ever learn anything new from, starting right now. A ratio between those two volumes of roughly 6%, meaning approximately 94% of everything currently visible to us has already, permanently, crossed beyond meaningful reach. A continuous, ongoing rate of loss, something in the neighborhood of 160 billion stars worth of galaxy, crossing that boundary every single year, right now, while you listen to this. And a specific mechanism behind that loss, not a sudden disappearance, but a slow, black hole-like fade, stretching each departing galaxy's final image across the remainder of cosmic time, redshifting it toward invisibility without ever quite completing the process from our own vantage point. Run the numbers forward, and the far future grows correspondingly stranger. By roughly 100 billion years from now, under the standard cosmological model, everything beyond our own gravitationally bound local group vanishes from any conceivable detection. The cosmic microwave background itself eventually redshifts into permanent undetectability, and an observer living in that distant era, doing their absolute best science with the most advanced instruments imaginable, would conclude, entirely reasonably and entirely incorrectly, that the universe has always been nothing more than a single, isolated island of stars. Every one of these numbers, taken individually, sounds like a story about loss, about things slipping permanently away, faster than we can ever hope to follow them. But taken together, they describe something quite different, something considerably warmer. Lawrence Krauss and Robert Scherer close their own 2007 paper on this exact subject with an observation genuinely worth sitting with, because it reframes the entire story we've walked through tonight, from something purely about disappearance into something considerably closer to a quiet kind of privilege. Their central point is this: we don't live in a privileged moment in cosmic history because the universe happens to be centered on us, or because anything about our specific location is special in any deeper physical sense. We live in a privileged moment because the knowability of the universe itself has an expiration date, and we happen to exist well before that date arrives. Consider what's still genuinely available to us, right now, tonight, that will not remain available forever. The cosmic microwave background is still detectable, faint but real, carrying direct evidence of the universe's earliest moments, still arriving after 13.8 billion years of travel. Standard candles, like the very type Ia supernovae that revealed dark energy's existence in the first place, remain measurable, letting us directly chart the universe's expansion history across cosmic time. Distant galaxies, even the 94% already beyond our permanent reach, remain visible for now, their old light still arriving, still fading gradually rather than having already vanished entirely. The entire observational foundation of modern cosmology, everything that ever let us discover any of what we've discussed tonight, is still, right now, actively, measurably present in our sky. An observer born roughly 100 billion years too late will inherit none of this. No cosmic microwave background left to detect. No visible neighboring galaxies rushing outward to measure. No expansion history to reconstruct. They will look up at a still, dark, apparently eternal sky and reasonably, carefully conclude that they live in the entire cosmos in its complete and final form, with absolutely no way of ever learning that a vastly larger, richer, more dynamic universe had once, long before their own existence, been fully visible and fully knowable to anyone patient enough to look. We happen to be alive while the shelves are still open, while the beach is still lit, and the distant ship on the horizon is still visible, even if we could never actually reach it now. While 94% of what has already, technically, left us is still faintly, patiently shining in our sky, its light still arriving, still telling us the story of a universe none of us will ever get to fully explore, but almost all of which we can, for now, at least still see. Almost everything is gone. And almost everything, for exactly this narrow window of cosmic time, is somehow, remarkably, still here. Picture it, one last time, before we close tonight. Somewhere, right now, tonight, in some direction you could point a sufficiently powerful telescope toward, there is a galaxy whose light left it billions of years ago. Light that has been travelling, uninterrupted, across an ever-widening gulf of space, arriving at Earth's telescopes at this exact moment, tonight, for the very first time. And somewhere, in the same instant, that same galaxy, its actual, present moment self, wherever and whatever it has become since that ancient light departed, sits permanently beyond our cosmic event horizon, sending us nothing more, ever again, its entire future unfolding in a place we will never be able to follow. We are not watching that galaxy disappear. We are watching its last photograph, still slowly developing, stretching gradually toward red and towards silence across the entire remaining span of our own future. Never quite finished, never quite complete, a fade without a final frame. And somewhere else, roughly 160 billion stars worth of additional light, an entire galaxy's population, give or take, is crossing that same threshold this very year, quietly joining the already vast majority of everything we can see that has already, technically, left us behind. Not with any explosion, not with any warning, simply drifting at the steady, relentless pace an accelerating universe imposes on everything within it, past a boundary that, once crossed, can never be uncrossed. 100 billion years from now, none of this will be visible anymore to anyone. The cosmic microwave background will have faded into permanent silence. Every galaxy beyond our own small, gravitationally bound neighborhood will have redshifted beyond any possible detection. Some future intelligence, living inside whatever remains of the Milky Way and Andromeda by then, will look up at a still, dark, uneventful sky and have no way of knowing that a whole living, expanding, richly populated universe once filled it, because we, right now, tonight, happen to be standing at exactly the moment when it still does. We are not the center of the universe. Nothing about our position in space is special in any physical sense at all. But we are, undeniably, standing in a very particular window of time. Narrow by the universe's own staggering standards, but wide enough, somehow, to have noticed. Wide enough to have measured the loss precisely. Wide enough to have understood exactly what it means, and exactly how fast it's happening, and exactly how much longer this particular view will remain available to anyone at all. That is not a small thing to have been given. Tonight we explored why the universe is expanding so fast that most of it is already gone, and what we found was not a single vanishing act, but an ongoing, measurable, genuinely active process. One that is happening, quite literally, tonight, while you listen. We found that the observable universe, the full 46.5 billion light-year record of everything whose light has ever reached us, is not the same thing as the reachable universe, a considerably smaller sphere, nested inside it, marking everything we could still ever learn anything new from. We found that approximately 94% of everything currently visible in our sky has already, permanently, crossed beyond that inner boundary, and that this figure keeps climbing, with something in the neighborhood of 160 billion stars worth of galaxy crossing beyond our reach every single year, right now, continuously, as the universe's own accelerating expansion drives the gap wider still. We found that the boundary most people mistake for the true point of no return, the Hubble sphere, where recession speed first equals light speed, isn't actually the real horizon at all. The genuine, permanent boundary sits farther out, defined not by simple velocity, but by the full, compounding future of an accelerating cosmos. We found that galaxies crossing that genuine horizon don't simply disappear. They fade exactly the way an object falling into a black hole appears to fade from outside. redshifting, slowing, stretching toward an infinity they never quite finish reaching, from our own vantage point, leaving behind a last, slowly developing photograph that will keep arriving, fainter and redder for the rest of cosmic time. And we found that this entire process, followed forward into the deep future, eventually leads to genuine silence. 100 billion years from now, under the standard model, nothing beyond our own small, gravitationally bound corner of the universe will remain detectable to anyone ever again. And cosmology itself, as an observational science, quietly ends. None of this is a story about failure or about a universe cruelly hiding itself from us. It's a story about timing, about the fact that we happen to exist during the specific, narrow, genuinely privileged window when the overwhelming majority of what's already, technically, gone is still faintly, patiently visible, when the shelves are still open, when the light is still on, when the loss, however vast, remains something we can actually watch, measure, and understand, rather than simply inheriting its finished, silent aftermath. Sleep well tonight, knowing that the sky above you, however familiar it looks, is quietly, continuously emptying, and that you happen to be alive during the one narrow chapter of cosmic history when nearly everything that's already gone is still, somehow, remarkably, still shining. Good night, and rest well under a sky that is, right now, tonight, more full than it will ever be again.